Hey everybody, welcome to week 12 of PS 398. So in the previous lectures, we have incorporated time into our book of fables in the hopes of trying to better model many important facets of international relations. We said, well, it seems like there are a lot of important situations where one player can observe what another player does prior to making her own choice. It might be that two factions in society get to see what the sovereign did, and thus after that can determine whether or not to coordinate on throwing the bum out. It could be that somebody receives an offer, so if we're playing ultimatum, you make an offer, I observe it, and then decide whether to accept or reject. It could be that one country decides whether or not to attack preemptively. So time is really important. I'm sure you've been waiting for me to tell you that. And throughout both the lectures on the subject and some of the provocative thoughts, I've alluded to the importance of infinite time horizons in some important results relating to whether or not states will cooperate with one another. And today is the day that I have to make good on those promises to discuss that particular topic. So today I want to talk about what happens, not if we're playing some tree game that goes on for some amount of time and then ends, but rather what happens if we take a simultaneous move game like we've studied before, chicken, assurance, prisoner's dilemma, etc., and we repeat it many times. In other words, what happens if we play prisoner's dilemma today, see what happens, condition what we're going to do tomorrow on what we saw today, play it again tomorrow, see what happens, condition what we do the day after that on what we saw the first 2 days, see what happens, and so on. So what happens if we get to repeat our interactions time and time again? Today I'm going to focus on the prisoner's dilemma, so let me motivate things a little bit more specifically on that. So in the prisoner's dilemma, there's a very stark negative result, right? So what happens in the prisoner's dilemma is both states have this strong, strict dominance incentive, right? So for both parties, defecting strictly dominates cooperation, and therefore the only IESDS surviving profile, the only Nash equilibrium profile, and so on, the only prediction that one would make from the prisoner's dilemma, played once, is that both parties defect. And you might remember that that's a very sad outcome, because that defect payoff that they get is Pareto dominated by the cooperate payoff. Right? Both parties do strictly better. Both states would do strictly better if they would manage not to have this arms race. Nevertheless, because of their individual level incentives, there's no way to make that happen if we play it once. However, I'm not sure if you noticed, but states persist over long amounts of time and have to think not just about whether or not what they're doing today is good for them today, but also on whether or not they are unnecessarily antagonizing other parties, or perhaps they're being too conciliatory and are not thinking enough about whether or not they will be hurt in the future by present conciliatory policies. In other words, these simultaneous move games that we studied in the middle of the class, they're fine. They're not part of trees necessarily. They're not part of extensive form games, but maybe we play them again and again and again. Right? Maybe every day is a new prisoner's dilemma for every pair of countries in the world. And an interesting question is, does that incentivize good behavior? Now, we don't have to be talking at the high level of international relations for that. One reason that we're nice to one another, if we're being honest with ourselves, one reason that we're nice to one another, and we don't do things that are short-term nasty like steal from one another, one reason we do that, among others, is that we know that we might see each other tomorrow. Right? So you signed up for a 15-week class, and if every week was a time that we played a game, do you want to irritate me in week 1 on the understanding that you're just going to, now you might do worse for weeks 2 through 15? No. You might be thinking about the fact that we have to see each other again and again and again. And that shadow of the future might be the thing that incentivizes good behavior, not because it's actually in your best interest in the immediate short term, but because the way that you relate today's payoff to the future might incentivize worrying about a long time horizon. Okay? Likewise with states who live much longer than we do. So today I'd like to do a relatively brief treatment of the infinitely repeated prisoner's dilemma. I'm not going to be able to show you all of repeated game theory, not that I've shown you all of anything up to this point, but I'm only going to be able to show you a very small sliver of a large literature that was very influential in political science, economics, computer science, and philosophy in the 1980s and 1990s, and has still, the relevance of the ideas persist, even if this isn't a super duper active area of research right now. This is a lesson that you will remember. This is something that you will remember having seen it. And so I hope that this particular fable, which we'll think about relatively extensively and only in isolation, I hope that this isolated fable is enough for you to learn the important lesson that the shadow of the future can incentivize good behavior even when the strategic incentives of the players seem to be at odds with cooperation. So I'm going to have to build this up slowly. So, one annoying thing about, not annoying, but the lectures up to this point have been like each block is its own relatively independent unit, right? So in the A block, we talk about one model. And then the B block, we talk about another model. And the C block, we talk about a third model or something like that. Whereas here, I'm going to be talking about one thing basically the entire time. I'm going to have to show a set of prerequisites, and then we'll talk about the core idea of the model, and then we'll talk about an interesting extension or the broad punchline that one gets from seeing the model. Let me stop being so cryptic. So in the A block, I want to talk about discounting. How do we work out the nitty-gritty? What are the details about thinking through how a state or somebody else might weigh future payoffs against the payoffs that they receive today? Okay? So if I'm playing a game with you and I get 2 happiness points for my equilibrium play today, and I would get 2 happiness points for my equilibrium play tomorrow, how much do I value that tomorrow to relative to my today to? How patient am I? How impatient am I? What's my time horizon? What's my shadow of the future? Okay? How much do I weigh future streams of benefits against my short-term incentives today? That's going to be the straw stirring the drink throughout the entire analysis, is the relationship between today's payoffs and the value of the future stream of payoffs, which depends quite intimately on how much I care about the future, right? If I knew that I was going to die tomorrow, I would just eat all of the meat that I could find and then a chocolate cake. Why? Because I don't value the future very much. I know I don't have much future to look forward to. I would enjoy all of the short-term benefits that I could while heavily discounting the future because I know it's not very important to me. Conversely, a state which does not have to worry about such mortal things might have a very long time horizon, might have to think very hard about future streams of payoffs conditional on what they did today. In the B block, I want to talk through the nitty-gritty of the infinitely repeated prisoner's dilemma and show you a couple of different equilibria in that infinitely repeated prisoner's dilemma. For the first time in what seemed like several weeks, I will have a couple of happy stories to tell you, albeit happy stories that occur only under certain scope limitations. We will discuss some famous strategies that one might employ in the infinitely repeated prisoner's dilemma, Tit-for-Tat, Grim Trigger, and so on, and demonstrate when they are and are not equilibria of that venerable game. And then in the C block, I want to show you the folk theorem of infinitely repeated prisoner's dilemma. Folk theorems are theorems that everybody knows are true and can be proved, but that nobody is the person that published it. Nobody actually published a paper that said, and here's this result. Everybody knows it's true, it never got published, so it's a folk theorem. So I want to show you the folk theorem of infinitely repeated prisoner's dilemma, which sort of takes the main lessons that we get from the B block and turns it into a way to think about what international institutions are and what function they serve. Holy crap, that got heavy in a hurry. And I think the folk theorem, it sounds a little wonky at first, but then once you internalize the main substantive punchline, it's a very beautiful result that is both maddeningly annoying and liberatingly beautiful at the same time. You will see that international institutions are both beautiful and ugly. I know, I wish I didn't have so many seemingly contradictory things to teach you, but life is confusing, it turns out. So I don't want to waste too much more time because we have a lot of model to get through today. I hope you enjoy this. Let's get started. So suppose I gave you $100. Don't get your hopes up. I'm not actually giving you $100. So an interesting question is, how many dollars is $100 worth to you right now? Don't overthink it. I'm not going to tell you to pause the video. If you're anything like me, if I gave you a $100 bill right now, that would be worth $100 to you. Let's not make this confusing. $100 bill, $100. Okay? Now suppose instead that I gave you a contract. I gave you a little piece of paper, and it said, I will give you $100 at this time next year. An IOU. It would be like a little contract that said, all right, you don't get any money just yet, but I'll give you $100 in the future. And suppose that I'm reliable. Let's just say that there's no issues of credibility on that. You know that I'm good for the money, and you know that I have no incentive to be mean to you or anything. I'm not trying to make that sort of point just yet. I'm just asking you, how much would you pay today? How many dollars would you give me today for a contract that was worth $100 in exactly 365 days? Pause the video now. What's that worth to you? What is that contract worth to you? It would give you $100 in 365 days. What would you pay for that? What would you pay for that? You might pay zero, right? You might say, you know what? I don't have time to waste. Life is short. Maybe I won't be here in 365 days, or all of my needs are very pressing. Maybe you're thinking to yourself, my needs at the moment are very pressing, and I don't have time to essentially save money by going to the rob bank, putting money in the rob bank, and waiting for interest in a year, right? You don't have time for that. $100 in the future is not worth $100 to you right now, probably, right? You might have said 50. Maybe you give me $50 today for the promise of $100 in a year. Maybe not. Maybe give me $80. Maybe you'd be willing to wait a whole year for $20 interest. For the record, that would be a 25% return on your investment, which is a very good annual return. But again, that might not be worth it to you. You might be thinking, I could have $80 worth of stuff right now, or a contract that would give me a 25% return for a year. There's no right way to weigh that, right? So in other words, what the future is worth to you in today units needs to be discounted. Okay? Whatever that proportion is, whether it was zero, if you would give me $0 for a contract worth $100 in a year, if you would give me $0, that means that you discounted next year's payoffs by 100%. So maybe you would multiply that $100 by a zero and say that's worth zero to me today. Okay? If you would be willing to pay $50 for that $100 contract, if you'd be willing to pay $50 for it, then that means that $100 is worth only $50, so you could multiply that 100 by 1/2, and you'd wind up with what it's worth to you today. If it was worth $80 to you, you could multiply that $100 by 0.8, and that would capture how much $100 was worth to you tomorrow relative to today. The future is worth 80% of the present to you. You discount the future at an 80% rate. Okay? Essentially, interest rates, or what you get on corporate bonds or other forms of bonds, where that's what happens, right? So if you buy a bond, or if your grandparents bought you a bond like mine had a penchant for doing, then what happens is you give somebody some money now, and they promise to pay some amount of money that's more over time in the future. And what the premium is, what the gap is, depends on how credible you think that the bank is, or how credible you think the company that you're buying a corporate bond is, or something like that. But it also depends on people's prevailing thoughts on future economic on the future economic situation. Also, it depends on how willing they are to save money compared to their current needs. All this to say, time makes value evolve in this discounty sort of way. And so what I want to show you before we get started is how we think about infinite streams of payoffs with discounting. So for example, let's consider how we would discount a revenue stream that was worth $1 every day for the rest of time. In particular, an interesting question is, how much would you pay for a contract that gave you $1 every day for the rest of time? 1 happiness point. We'll just keep it in utils. Let's say that you got 1 happiness point worth of money every day for the rest of time. Now, in expectation, there's no probability. So just add it all together. Today I get 1, tomorrow I get 1, the day after I get 1, the day after that I get 1. I get 1 every day. That is worth infinite dollars. But would you pay an infinite amount for that? I wouldn't. I wouldn't pay an infinite amount for that. For $1 every day for the rest of my life, I don't think I'd pay more than $10. That might be a stupid decision on my part. But I need that money now. I have needs. Chewy needs to get to college. Right? I'm running out of light bulbs for this stupid lighting for these movies. I have needs. There's a new Assassin's Creed game coming out. I have needs. I don't want $1 every day for the rest of my life. I want enough money to buy the Assassin's Creed game before the holiday break. So how would I model the fact that I wouldn't pay infinite money for an infinite revenue stream? Well, what I'd say is I don't care about the future that much relative to today. All right? So I want to know, I want one number that tells me in the units of today, the dollars of today, the utils of today, the happiness points of today, I want one number that tells me how much that contract is worth. That contract to get $1 every day for the rest of my life. Well, the way that we do that is by introducing a term called delta, which is the discount factor. Delta is the discount factor. And the idea is that I'm going to have some delta that lives between 0 and 1. And delta means how much is tomorrow's happiness worth to you in today points. So I'm going to say that I have an infinite time horizon. So I'm going to be able to choose some little t that tells me the time period. Little t is the time period. T equals 0 is today. T equals 1 is tomorrow. T equals 2 is the day after tomorrow. T equals 3 is the day after that. Okay, so I'm gonna index time with this time horizon. It's just gonna be the counting numbers including 0. Today is t equals 0, tomorrow is t equals 1, and so on. And I'm gonna use this discount factor, this number somewhere between 0 and 1, to model how much the future is worth to me, how much each day is worth to me compared to today in today units. You'll see what I mean here in a second. So if t equals 0, my multiplier, my time coefficient, is going to be delta to the 0th power, which is 1. So the present is worth 100% of the present to me. In t equals 1, tomorrow, I'm going to say that tomorrow is worth delta to the t equals 1. Delta to the 1 equals delta of the, that's worth delta. It's a delta proportion. In other words, $1 tomorrow is worth delta dollars to me today, where delta is less than 1. Delta is less than 1, which means maybe I would pay $80 for a $100 contract if delta equals 0.8. The day after tomorrow is t equals 2, and that is worth delta to the 2 to me. Delta times delta, and because delta is between 0 and 1, that's smaller. That's going to go down. The idea is that the future is going to go down. So today is worth delta to the 0. Tomorrow is worth delta to the 1. The day after that is worth delta to the 2. The day after that is worth delta to the 3. That's going to lead to this geometric decay, right? So here's 1, here's delta squared, here's delta cubed, here's delta to the 4th. It's going to go down like that. So that each day of the future matters to me, but it matters to me less and less. The future payoffs decay, because there's so many things that I could do with those resources. I might not want to save. Okay, so I value the future at this decaying rate in this version of the model. This is how we model repeated games or other dynamic games over time, is by saying, well, the future just matters less. Now look, if delta equals 0, then today is worth 0 to the 0, which is still 1. So today matters to me just as much as it ever did and does. Tomorrow matters to me 0. The day after matters to me 0. The day after that matters to me 0. So in other words, if delta equals 0, then I am perfectly impatient, and we might as well be playing the game once and only once. Right? If delta equals 0, then it's just a 1 and a bunch of zeros after that in terms of how much I value that dollar every time. In other words, if delta equals 0, then a contract that pays me $1 every day for the rest of my life is worth $1 to me. That dollar that I got today. Tomorrow means nothing to me. I have a devil-may-care attitude. I don't quite know what that term means. I probably just misused it, but it's week 12, so just go easy on me, okay? I'm so loopy by now. Conversely, if delta equals 1, then that means that every day of the future matters just as much as today does. So that contract for $1 every day for the rest of my life is worth infinite money to me. Every day matters 1 to me, because 1 to any power is still just 1. There's no decay at that point in time. Right? Delta equals 0 means 1 and then a bunch of zeros. Delta equals 1 means it's 1 every day. And somewhere in between means we have this decay thing happen. So this discounting is the way that we address the possibility of the future not mattering as much as the present. It's the way that we model patience. It's the way that we model the shadow of the future and how much it matters to a given player. If you're thinking about this in terms of money, delta is related to interest rates, right? So if the current interest rate is, I don't know, like 3% or something, if the current interest rate is 3%, then we could come up with a delta that pins that down. So if the interest rate is 3% on money, then delta equals 1 over 1.03. If the interest rate was 10%, it would be 1 over 1.1. It's just 1 over 1 plus r. So if you can think in terms of interest rates, you can think in terms of delta as a discount factor. And vice versa. If you can think in terms of delta, you could back out the appropriate interest rate. However, in terms of utils, there's no bank that just takes in utils. There's no bank that takes in happiness points and then gives you happiness points in the future. That's weird. Don't do that. So now let's think about this stream in terms of util. Let's say you were getting 1 happiness point every day for the rest of your life. What would be the associated dynamic utility? What would be the continuation value? What would be the value of that series of 1s? What's the value of that series of 1s? You're getting one happiness point every day. What's the sum of that? I want to know delta to the 0 times the 1 you got today, plus delta to the 1 times the 1 you got tomorrow, plus delta squared times the 1 you got in 2 days from now, plus delta to the 3rd times the 1 you get 3 days from now, and so on. I want to know, what is that sum? That sum is going to be how much this contract is worth to me, given my patience, given my delta. Okay? Now I'm going to do a bit of a magic trick. I can derive this in the meetings if you want me to. I'll do a little magic trick here to show you that this is actually relatively tidy. If we're playing this game every day for the rest of our life and I'm getting 1 happiness point because of some equilibrium behavior chosen every day for the rest of my life, if I'm getting 1 happiness point every day, then my sum, the sum of my series, the sum of my infinite series is 1 over 1 minus delta times 1. So just to animate things, let's say that delta was 1/10. So delta equals 0.1. So that means I don't value the future very much at all. I don't value the future very much at all, okay? If delta equals 0.1, that means I don't value the future very much compared to the present. And so my contract, which is worth 1 happiness point every day, gives me 1 over 0.9 times that same 1, that same happiness point, which means I get 1.111111111 repeating 10/9 of a happiness point. So you get to take that and multiply it up a little bit. But think about it. This is worth 1 happiness point every day for the rest of my life. And what I'm saying is, that's great. I don't care about the future that much. And so the only perk that I get out of this is like 0.11111111111. Because I got that 1 happiness point, subtracted it away. That means that the only perk of the future is 0.11111111111. Because I don't value the future very much, that infinite stream isn't the benefits of the infinite stream aren't worth very much to me. Conversely, suppose that I value the future a lot. Let's say that my delta was 0.9, so that every day was worth 90%. Every tomorrow was worth 90% of its respective today. Well, if I care about the future a lot, with delta equals 0.9, then 1 divided by 1 minus 0.9, which is 1 divided by 0.1, that's 10. So in other words, this contract that gives me 1 happiness point every day for the rest of my life is worth 10 happiness points to me. I would give up 10 happiness points today to get that contract. The other contract, if I didn't care about the future, I would only give 1.11111 happiness points. So in other words, how many happiness points I would pay to get a contract worth an infinite stream of things depends on how patient I am, how much I discount the future. Now, what's the motivation for discounting? I've been framing it as patience. And that's a perfectly reasonable way to frame it. And maybe countries can have varying degrees of patience, even though they know that their future time horizon is very long. Because countries don't die, maybe they value the future a lot. The political leaders get voted out of office. Their tenure in office has mortality, even if the institution doesn't. Right? So presidents can only be in office for so long. And so maybe their decisions reflect a mix of both what they think is best for the country, which has a long time horizon, and what is best for them as a politician, which has a shorter time horizon. And so there's some interesting mix of this human element and this institutional element. However, even without the human element of leaders, suppose that we just thought that there was some probability of the contract breaking down. So I've been talking about this contract as if it's perfectly reliable, but it might not be. Maybe there's an 80% chance that it breaks down. Maybe every day the contract survives only with probability 0.8. Well, then that would be equivalent to having a delta of 0.8. Okay? So it could be patience, but it could also be thoughts on the reliability of the stream. If you think there's some probability of breakdown, that's essentially the same as being impatient. Whether it's because of genuine impatience, like, give me the cookie, I just want a cookie, or impatience that becomes because you think that this might break down, either one of those are equivalent in terms of how they play with this delta idea. Either way, that seems realistic to me. Whether it's about people or countries or other sorts of institutions or groups or whatever. Nobody, not even a state, is patient enough or sanguine enough about the future to think that tomorrow is worth 100% of today. Nobody is that patient, not even a state. Now, there may be some people that have delta very small. It could be that humans or states could have low patience, incredibly low patience numbers. They could have delta very small, delta very close to zero. That might be because of expediencies of the time. It might be because of low faith in the quality of institutions and whether or not that stream of ones is actually going to happen. There's all sorts of different reasons that you might have low patience. But I think that most people would agree that a delta of exactly 1, where you value the future exactly as much as today, it seems reasonable to say that isn't true. Okay? And an interesting question is what sort of institutions or what sort of situations would be those that inspire high deltas, high patience or high confidence, versus situations that have low deltas, low patience or low confidence. And because of this probability of breakdown thing, there's actually a somewhat more realistic interpretation of the infinite time horizon. I think the idea here is, the infinite time horizon, it might seem, and I mentioned this in a provocative thought a few weeks ago, it might seem like we're actually thinking that we're going to get that dollar every day for the rest of time. That's what the infinity there is buying us. But because there's just some probability of breakdown that animates delta, if we use that means that things will eventually come to an end. It's just that we don't know on what day, right? So let's say that we think the probability of breakdown is 0.5 every day, okay? So here it is today, we're okay. The probability that things break down tomorrow is 0.5. The probability that things break down in 2 days is 0.5, the chance that we survived to make it to 2 days, times 0.5, 0.25, and so on. This actually winds up creating a geometric distribution over the possible outcomes, where it's like Yeah, it is possible that we could be bargaining every day for the rest of time, but chances are excellent that this will break down eventually. Right? It might break down on day 1, it might break down on day 2, it might break down on day 3. That still requires humility on the analyst's part because we don't know when that breakdown is, so we have to proceed as if it goes on forever, and there's just some random chance that it breaks down on any given day. I can't tell you for sure that things are going to break down on day 10, but I can give you a probabilistic expectation that it will make it to day 10. What are the odds that it breaks down exactly on day 10? Those are sort of introductory probability theory questions. So a lot of this, it seems as if we're modeling with some hubris about this infinite time horizon, but in reality, it's more like we don't quite know when the end is going to be. We have to proceed as if things are as if things are infinite, and then we can motivate delta either as the more intuitive patience term or as a somewhat less intuitive, but maybe better in the context of the model, probability breakdown term. And either way, we have a nice way to think about uncertain time horizons, if not infinite. So now that we have this pinned down, and I know this is a little bit boring, don't get too nervous. We're going to use this to study the infinitely repeated prisoner's dilemma over in the B block, so I'll see you there. So before we think about repetition, let's just revisit our friend the prisoner's dilemma. Remember when that was something we were doing? I do, barely. It was like 3 weeks ago. So the first thing I'm going to do, just to make the math a little bit easier, is I'm going to take this prisoner's dilemma as we've drawn it, and I'm going to subtract 2 from every payoff. The idea here is I want the defect payoff to be worth 0 happiness points. Okay? You'll see why when we get to it. So now, defect is 0, 0. Cooperate is 1, 1. Cooperate defect is minus 1, 2. And defect cooperate is 2, minus 1. And it still is the case that the unique Nash equilibrium of this game is defect, which gives an equilibrium payoff of 0 happiness points apiece. And this is the most compelling, most tragic, most awful story of all of the 2x2 games. Genuinely tragic, right? Inspired international relations thinkers, political philosophers, all sorts of different people. This has launched a lot of different thoughts on the subject, the tragedy of the prisoner's dilemma. So now suppose that we decided as modelers to think about playing this game every day for the rest of time. So today we play prisoner's dilemma. And then tomorrow we play prisoner's dilemma. The day after that, we play prisoner's dilemma. The day after that, we play prisoner's dilemma. And so on. And so forth. Etc. 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 I think I just ruined that show for you, right? And every time that we play, we get to observe what happened. So we play Prisoner's Dilemma today, and then we see what happened. And we'll be able to condition what we do tomorrow on what happened today. It's sort of like an extensive form game. You could draw this with trees and information sets real careful like if you wanted to, but this is only 4K, and I don't really have enough room to get an infinitely repeated Prisoner's Dilemma out very far. Infinity is big, as we learned the hard way last week. Now just think about the payoff for playing defect every day. Let's just say we were playing defect every time. Well, that means if I was using this discounting thing, then my utility for that would be delta to the 0 is 1 times 0 is still 0, plus delta to the 1 times 0 is still 0, 0, 0, 0. It's worth 0. If we had defect every day for the rest of time, that would be worth 0. If we managed to play cooperate every day for the rest of time, if we managed, then we would get delta to the 0 is 1 times 1 is 1. Delta to the 1 is delta times 1 is delta. Delta squared times 1 is delta squared. We would wind up with 1 over 1 minus delta times 1. Okay? So an interesting question is, how can we think about strategies in ways that allow us to think meaningfully about comparing this 1 over 1 minus delta times 0. How do we meaningfully come up with a strategy that might animate that? What's a strategy in this game? Well, let me show you one. A very well-known strategy in a game like this is called Grim Trigger. All strategies in games like this sound like computer programs, which is interesting because when this all started to get studied in the late 1970s and early 1980s, Robert Axelrod ran some computer tournaments back when home computers were a pretty rare thing. And people sent in strategies that were computer programs, and then he put them into tournaments to see which ones did best. So a strategy is a computer program that has an initial state and then as many ifs thens as you would like it to. Let me show you Grim Trigger. So Grim Trigger has an initial condition of cooperate. So at the beginning of time, you play cooperate. The initial state, the initial condition is cooperate. And in every single subsequent round, if anybody has ever defected in any previous round, then you defect every day for the rest of your life. And if nobody has ever defected in the previous time, keep cooperating. So in other words, this is an infinite punishment mechanism. Grim Trigger says, all right, I'm going to start off cooperating. But if you ever defect, or if I ever defect, but according to my initial state, there's no reason I would defect other than you defected. So the idea basically is, I will cooperate. And if you defect ever, I will defect every day for the rest of time. I will punish you every day for the rest of life. This is my vendetta strategy. I'm going to hold a grudge forever. I'm going to have an infinite grudge. Grim Trigger is an infinite grudge strategy. Interestingly, this takes this infinite horizon interaction that we're talking about, today, tomorrow, the day after, and every day, infinite amount of time, and it makes a reasonable strategy. All it does is it gives you an initial condition, and then it partitions every possible trip through the game into two states. State 1 is nobody has ever defected, and state 2 is somebody has defected. This is how computer programs are written. So that's the Grim Trigger strategy. Cooperate, and if anybody has ever defected, defect for the rest of time. Otherwise, keep cooperating. An interesting question is Grim Trigger an equilibrium against Grim Trigger? Let's say that I was playing Grim Trigger and you were playing Grim Trigger. I want to know, does either of us have an incentive to deviate from Grim Trigger? Not from cooperate, not from defect, not from chicken swerve, not from chicken straight, not from an individual decision, but from this broad program that I've written. I've just drawn a computer program that is my strategy for the rest of time. It's kind of heavy when you think about it, right? Now, you might be thinking, how the heck am I going to figure out if there's an incentive to deviate from Grim Trigger? Let me show you. There's a very excellent trick. Wonderful trick that is one of the great saving graces in repeated games, in dynamic games more broadly, stochastic games, a whole class of game theory. This is important in computer science and in macroeconomic theory and some different parts of applied mathematics. The thing I'm about to show you, it's not as cool as Arrow's theorem. It's not as important as Nash's theorem for game theory. But this is one of those cool trick things that is a big deal. Okay, and this is called the one-shot deviation principle. And what it says is, if I want to check to see whether or not something is a best dynamic strategy, a best computer program, then I don't have to check every deviation on every day. Think about it right now. Do I have to check to see if I want to deviate on day 2, deviate on day 3? That's too many deviations to think about. I don't want to think about every single deviation. It's to be impossible for me to think about every single deviation, the same way it was impossible for me to solve my sliver of the hoodie last week. I can't do that. So how am I going to evaluate this? I'm going to check for a single shot deviation. The idea of the one-shot deviation principle is that if nobody has an incentive to deviate in one round and then immediately revert to the strategy in question, if nobody wants to deviate then, if we've appropriately thought through what will happen, then we're good. So let's think about, I'm going to use a little table to demonstrate what happens if we both play Grim Trigger against one another every day for the rest of the time, no deviations. Okay? Well, on day 0, I cooperate and you cooperate. On day 1, I cooperate and you cooperate. On day 2, I cooperate and you cooperate. If neither of us ever deviates from Grim Trigger, then we both cooperate for the rest of time. We get 1 happiness point every day for the rest of our life, and we both get 1 over 1 minus delta happiness points. That was that trick. There's a reason the A block was there. Now consider the situation where you're playing Grim Trigger every day, just like before, and we're going to think about what happens if I deviate on day 0. And we're going to have to do this thinking about all of the possible histories, all the possible things that could have happened yesterday. There are 4 different things that could have happened yesterday. It could be CC, it could be CD, it could be DC, and it could be DD. So we're going to have to think about all 4 of those in turn. Don't worry, you'll see. This is all by way of example. I just want you to get this heuristically. I just hope that you can remember some of this, okay? You're not going to solve this. So consider what would happen if on day -1, I'm just using a trick here to say day -1 is a reasonable thing to talk about. I just want to keep the math easy. And you're like, you're failing. I know. So let's say we woke up, and on day -1, it was cooperate. And we're both playing Grim Trigger, but I wake up on day 0, I have a bad day. And I deviate from Grim Trigger on day 0 and day 0 only. I just have a fluky day. I have a fluky 1 bad day, and I deviate from Grim Trigger. And then we have to think about what that would generate conditional on us both reverting to Grim Trigger after that. Okay? So, I wake up, I have a bad day, I defect. Why? Because day -1, it was cooperate. Clearly nobody has ever defected. I'm the one that starts it. This is my freak mutation of a bad day. I defected. Okay? And you cooperated. Because you never deviated. We're checking to see if I have a profitable deviation by having this 1 bad day. So that means on that 1 day, I get 2 happiness points, and you get -1. And then I wake up the next day, miraculously cured of whatever was bothering me on day 0. And you never had anything to cure. You just keep playing Grim Trigger. So suppose now that we just, on day 1, day 2, day 3, every day for the rest of time, we decide to go back to Grim Trigger. I'm just checking for a 1-shot deviation. Day 0 was my 1-shot deviation. Okay? Well, let's think about what that means. Well, you're playing Grim Trigger, and I'm playing Grim Trigger. Well, now one of us has defected. I defected on day 0, so you're going to defect for the rest of the time, and so am I. Day 1, you defect, and so do I. Day 2, you defect, and so do I. Day 3, you defect, and so do I. We're playing Grim Trigger. We're going to defect for the rest of time. Okay. So now we are defecting. Those defect got 0. There's a reason that we did that. So defect yields 0 happiness points. So in other words, my payoff for my 1-shot deviation was the 2 that I get multiplied by delta to the 0 equals 1. So I got 2 happiness points in the immediate short term, but that caused an infinite stream of zeros thereafter. Okay? So now let's check to see when I wish that I had not deviated in the first place. So I want to know when 1 over 1 minus delta is greater than or equal to the 2 that I get for that 1-shot deviation off of a CC. Well, that means that I want to know when is 1 over 1 minus delta greater than or equal to 2. Algebra. That means delta greater than or equal to 1/2. So if I'm sufficiently patient, then I don't want to deviate from Grim Trigger following a CC. Let's suppose instead that the history going into my deviation day was I was cooperating and you defected. So suppose that a day -1, I cooperated and you defected. Okay? And now it's deviation day. I'm going to deviate from Grim Trigger on this day. I'm the deviator. All right? So right now, you're in time period 0, you're defecting because somebody has defected in previous history. So you are defecting. And I'm going to decide to try to deviate from Grim Trigger by cooperating. That's a deviation because I'm supposed to I'm supposed to defect on you. I'm supposed to defect. Grim Trigger tells me that because you deviated in the previous history, I'm supposed to defect right now. You defected at time -1. Grim Trigger tells me to defect. So in order for me to deviate for this 1-shot, this 1 deviation day, in order for me to deviate on deviation day, I have to cooperate. So in other words, at that time period 0, You defect and I cooperate. I get -1 happiness points. You get 2. You're like, wow, this is great. I got away with 1. And then we revert back to Grim Trigger after deviation day. Well, that means a steady stream of zeros. So in other words, my payoff for this one-shot deviation after a CD profile is -1, which can't be higher than 1 over 1 minus delta. So there's no profitable deviation in terms of deviating after a CD. Same logic goes after a DC, right? If we came into it and in time period -1, I had defected and you had cooperated, well, then you're going to defect on deviation day because somebody defected prior to that. I'm going to deviate from that by cooperating that one day. That gets me -1. That's no good. And the same goes after a DD as well. After a DD, you're going to defect on deviation day, and now I deviate by playing cooperate, I get -1. So in other words, magic is about to happen. Magic is about to happen. Magic is about to happen. Grim Trigger is a subgame perfect Nash equilibrium against Grim Trigger. Grim Trigger v Grim Trigger. That's a Nash equilibrium, subgame perfect Nash equilibrium, so long as delta is greater than or equal to 1/2. If our players are sufficiently patient, then this punishment mechanism is enough to incentivize good play. Because if they maintain Grim Trigger forever, they cooperate every day, today, tomorrow, etc. for the rest of time. We just took the Prisoner's Dilemma, the saddest story of them all, and made it a happy story by making the future matter. So long as our players are sufficiently patient, so long as they value the future at delta greater than or equal to 1/2, so long as they care enough about that stream of benefits of good behavior, they can cooperate today. Now think about how delta changes across all sorts of different contexts. Prisoner's Dilemma can be about arms races, in which case patience isn't really much of a virtue. It can be about environmental politics, where patience is a massive virtue. So depending on what we're potentially Prisoner's Dilemma-ing over, delta may be high or low, which means the Grim Trigger may or may not be a saving grace. So that's Grim Trigger. Grim Trigger against Grim Trigger is a Nash equilibrium so long as our players are sufficiently patient. That's pretty great. Notice that this requires an incredibly heavy-handed punishment mechanism, however. Right? We are putting people in jail for longer than life. Right? This is, if you ever defect, I will never, ever, 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 ever cooperate with you ever again. Grim Trigger is a one chance. You are being, if you ever do the wrong thing, then you are punished forever. I'm not going to work through the analysis for another strategy, but I want to show you another strategy. I want to show you a very famous strategy referred to as Tit-for-Tat. Tit-for-Tat is like Grim Trigger in the sense that it's a punishment strategy. If you ever defect, I will defect. But instead of saying I will defect for the rest of time, Tit-for-Tat goes to the other extreme and says, I will defect for 1 round. I'll punish you for 1 round. You're in the penalty box for 1 round, and then I'll go back to cooperating. So Tit-for-Tat says the initial state is cooperate, and then if your opponent defected in the previous round, then you defect for 1 round, and then you revert to cooperation. So let's think about what a one-shot deviation would induce from a CC history. So suppose that the day before deviation day, we both cooperated. That's our initial condition, right? Our initial condition is both cooperate. So this is what happens if we were playing Tit-for-Tat at the beginning of time. This is what would be happening. And then deviation day comes, and I decide to deviate. I have a bad day, and I defect. So it's defect, cooperate. On deviation day, I defect, and you cooperate. The day after, I revert to Tit-for-Tat. I had 1 bad day, and you never had a bad day, so you're going back to Tit-for-Tat, and I'm going back to Tit-for-Tat. Well, now, the day after deviation day, I go back to cooperating because you didn't defect in the previous time period, but now you defect. And then the day after that, you go back to cooperating, but now I defect. And the day after that, I go back to cooperating, but then you defect. So in other words, Tit-for-Tat induces these little CD, DC, CD, DC, CD, DC, CD, DC. It makes these little cycles of snark. I punish you for a day, you punish me for a day. I punish you for a day, you punish me for a day. I don't want to show you all of the associated math, but that isn't a profitable deviation so long as we're sufficiently patient. So long as we're sufficiently patient, we would rather have a steady stream of ones than have 2 minus 1, 2 minus 1, 2 minus 1. Where the big question is that 2 on deviation day, is that full 2, is that enough to outweigh the 2 minus 1, 2 minus 1, compared to the steady stream of ones that you get every day for the rest of time if you cooperated? Okay? So long as delta is greater than or equal to 1/2, there is no profitable deviation from CC. What about CD? This is when things get real tricky. So suppose we went into this and it was CD. I cooperated and you defected the day before deviation day. Now it's deviation day. Now I cooperated the day before deviation day and you're still playing tit-for-tat on deviation day, so you still cooperate. But now I'm supposed to defect on you. I'm supposed to punish you on deviation day and I don't. Suppose I didn't. So now I cooperate. Now we're both cooperating. My deviation just brought on a virtuous cycle of ones. Which is exactly the thing that we just said was better so long as our players were sufficiently patient. And actually what winds up happening because of this, and you could work out the same thing happens everywhere, DD there's no profitable deviation because you don't just want to cooperate for one day. So for all the other 3 histories, the players can induce cooperation by deviating, which means that we don't want them to be too patient. So we want them to be patient enough that they don't initiate the problem, but not so patient that they miraculously create cooperation where there was supposed to be a cycle of CD-DC. And in fact, in this model as I've written it down, and I'm just trying to spare you some of the sausage making, tit-for-tat is a subgame perfect equilibrium only when delta is exactly equal to 1/2. So Grim Trigger works for every delta greater than or equal to 1/2. So long as the players are sufficiently patient, then Grim Trigger is a subgame perfect equilibrium. Tit-for-tat is at exactly 1/2. Then a 1-period punishment strategy is best. And actually, every intermediate punishment mechanism, I punish you for 2 years. I put you on probation for 18 months. I give you 10 to 25. I give you 25 to life, no parole. All of those intermediate sentences, all those intermediate amounts of punishment. I defect for 2 rounds. I defect for 5 rounds. I defect for 10 rounds. I defect for 1,000 rounds. Every one of them induces a range that starts at 1/2 and goes up to some upper bound, because otherwise you would want to be the person that creates cooperation. If you were too patient, then you wouldn't want to punish for only 1 round. So remarkably, Grim Trigger works a lot. Punishment Forever works a lot. Now that's not as good as Tit-for-Tat in terms of the payoffs for our players, but that isn't the question. And then intermediate punishment mechanisms require intermediate amounts of patience, where there's an upper bound on how patient you can be and a lower bound on how patient you can be. But so long as our players have appropriate amounts of patience, so long as they think the probability of breakdown is in a sense intermediate, then we can come up with punishment mechanisms that generate good behavior in this awful tragic story of the infinitely repeated prisoner's dilemma. The shadow of the future creates cooperation. That's a happy story. Now, who decides which punishment mechanism we're using? Who decides which strategy and how long a punishment ought to be? What decides that? Well, in domestic politics, it's the state. There are laws saying if you do a certain wrong thing that is in your immediate short-term interests, we will punish you for some amount of time so that your stream of benefits in the future is bad enough that hopefully this incentivizes good play today. We want you to do nice things today, even if they aren't in your immediate short-term interests. We do that because there's some threat of punishment in the future. In international relations, it's a lot trickier. right? Nobody announces, I intend to punish you for 4 years. Nobody ever says something like that. But international institutions play a big role in that. They say, well, there's certain kinds of defection that we don't like. There's war that we don't like. There's genocide that we don't like. There's human rights violations that we don't like. There's all sorts of things that might seem short-term expedient to a country or the leader of a country or something like that might be the best thing to do on deviation day. You get that one goodie today. And what institutions do, domestic or otherwise, is they say, okay, then we're going to alter your shadow of the future by announcing a credible punishment strategy. I could do the same thing with positive reinforcement too. So in Prisoner's Dilemma, I don't have any happy equilibria to play with, right? I don't have any really happy outcomes to play with. But it could be that there's some carrot that I offer you instead. If you are good today, then I will offer you benefits in the future. So Grim Trigger is a punishment mechanism that's especially well suited for infinitely repeated Prisoner's Dilemma. But if we were playing infinitely repeated Stag Hunt, where there was a sad equilibrium and a happy equilibrium, maybe we could promise to play the happy equilibrium every time for the rest of time if you were good. So that would be not Grim Trigger, but with the opposite of Grim Trigger. But the idea here, and this is broader than just IR, but it's especially relevant for IR, is that your short-term incentives, we can adjust them. If we repeat our interactions, that gives an opportunity to credibly and reliably adjust your future streams of payoffs with other actors with whom you are strategically embedded. That's a huge point. Right? This was a huge point. When this first got made, when people started to think about this in the 1980s, they realized that a lot of the grim stories that one might tell after reading a lot of realism and looking at the Prisoner's Dilemma and saying, oh my God, everything is an arms race, and the arms race is all a Prisoner's Dilemma, and so we're screwed. Well, maybe not. Maybe the shadow of the future matters in happy ways. It's plausible. It might not be true, but it's plausible. There are good equilibria out there. Now it's a matter of finding them. We're going to dig into that idea pretty deeply in what's coming in the C block, so I'll see you over there. So I don't want to spend too much time on this. We're already pretty late into the lecture, I think. And I really just want this to be a fun, substantive idea for you. And you're like, oh, this has been so fun and so substantive, Rob. I know. So I just want to show you one cool thing. So what I want to do first is I want to take the Prisoner's Dilemma and I want to put its pure strategy profiles into a utility imputation space. So given the way that we've drawn the utilities, there's a dot for defect effect at 0, 0. There's a dot for cooperate at 1, 1. There's a dot for cooperate defect at -1, 2. And there's a dot for defect cooperate at 2, -1. So we have this utility imputation space. And I want to animate this as every sort of time averaged payoff, the value of every time averaged, sort of today's payoff averaged with tomorrow's payoff, sort of a time normalized payoff. The idea here is I want an infinite stream of 2s to be worth 2. So what I'm going to do is I'm going to multiply everything by 1 over 1 minus delta to come up with normalized streams of payoffs. You'll see what I mean here in a second. So in other words, if we played defect every day for the rest of time, that would give us a time normalized vector of utilities that was exactly at 0, 0. Similarly, if we play cooperate every day for the rest of time, then we would get 1, 1 instead of 1. I'm just going to multiply everything by 1 minus delta, and that's just going to normalize all the payoffs so that we can talk about them in today units instead of these weird future time stream ideas. So here's my utility imputation space. Now I'm gonna perform a multi-step procedure to come up with an interesting shape here. All right. The first thing I'm going to do is I'm going to link all of the dots. All the outside, I'm going to link the outsides of the dots with lines. Okay, so now I've made this weird polygon. Sort of like a diamond on its side. Okay. That's step one. This is referred to, the fancy term for this is called the convex hull. This is the set of all combinations of these 4 points. I could come up with a combination of these 4 points and pin down every point in this set. Convex hull. Every possible convex combination is what they go. That's all it is. Every pair of lines that I could draw between 2 points. It's not a big deal. The second thing I'm going to do is I'm going to perform some surgery on this diamond. So I'm going to perform some surgery here. So I'm going to get rid of everything worse than 0 for player 1. That's everything to the right of this axis. I'm just going to chop it off. I'm just performing some surgery. I don't care about the equations here. I just want you to see a point. This is a really important point I'd like to make. And similarly, I'm going to perform some surgery. I'm going to chop off everything worse than 0 for player 2. That's everything in this little triangle below this axis. I'm just going to chop it. And the reason that I'm chopping at 0 is that 0 is an equilibrium, is the only equilibrium here. All right? So in other words, you can always play defect-defect. It's always an equilibrium. And so you're never going to do worse than that in any equilibrium because you would just deviate to defect-defect. If there was some equilibrium that was offering you -1 in moving forward every day for the rest of the time, why wouldn't you just defect to deviating? Your opponent would deviate and we'd be deviating forever. You'd be getting 0 every day for the rest of the time. So we don't want to consider those things that are worse than your worst equilibrium, which in the prisoner's dilemma, there's only one. So I just chopped off everything worse than 0. So now I have this little... It's a weird looking shape, right? I have this weird looking shape. And this is every possible utility imputation where it's at least as good as defect-defect for both players. So just to call your attention, here's one that gives both players 1/2 every day for the rest of the time. It offers them an average of 1/2 every day. Their expected payoff every day, over time is 1/2. There's the one that gets them 1 every day. There's the one that gets them 0 every day. There's one that gets player 1 0 and player 2 1/2. There's one that gets player 2 0 and player 1 1 1/3. That's in there. That's all. They're all in here. Look, there's a massive number of utility imputations in here. Each one of these is a possible distribution of happiness over time. We just saw the Grim trigger, if delta was greater than or equal to 1/2, would get us exactly at the cooperate dot. So these are all the possible happiness outcomes. I haven't said anything about equilibrium yet. So let me tell you something really interesting. This is the Folk theorem for infinitely repeated games. For every element of this set, every utility imputation that's in this convex hull and where everything is better than your worst equilibrium payoff. So everything in this shape that I created through this multi-step process, everything in this shape, 1/2, 1/2, 1, 1, 1 1/3, 0, 0, 1 1/3, etc. For every one of these, there exists some delta sufficiently high, some amount of patience, some high enough amount of patience. There exists some amount of patience that's high enough that generates that utility imputation as the equilibrium outcome of some subgame perfect equilibrium. In other words, every part of this shape is a possible equilibrium outcome in terms of happiness points. Every single freaking one. 1 1 is a possible outcome. 0 0 is a possible outcome. 1 and 1/3 0 is a possible outcome. Pi over 1 plus pi, pi over 1 plus pi is a possible outcome. They're all possible outcomes. They're all possible equilibrium outcomes. Every single possible utility imputation in this shape, every possible happiness distribution in this shape is a possible outcome of an equilibrium of infinitely repeated prisoner's dilemma for some sufficiently high amount of patience. Every one of these is possible. Every single one of them is a possible outcome. Now, what does that mean? We got to pick one. What's going to do that? An institution. What international institutions do, among other things, is they choose one of these happiness situations. Institutions are a social planner and a bargaining problem, but that bargaining problem is far deeper than the static one that we had before. They choose the happiness outcomes in this dynamic sense, in a world that seemed like it was going to be nasty. Now there's all these beautiful, rich possibilities, all of which are better than the nasty 0-0 outcome. But now we have the onus upon us of setting the happiness for somebody. An institution is a social planner that solves this equilibrium selection problem and takes us from, oh my goodness, single shot prisoner's dilemma, there was nothing to choose over, we were dead. Now we have an embarrassment of riches, but we have this terrible decision to make. Which of these are we going to choose? Now notice that if delta was low, then I would just have a smaller range. It would be closer to 0-0. If I didn't have very patient players, if I had impatient players, then I couldn't make 1-1 be a good outcome. But maybe I could get closer than I could do better than 0-0. So more patience, more possibilities. But I still got to pick. I still have to come up with normative criteria to pick. Or some other criteria. Maybe just the powerful countries design an institution that makes all the less strong countries as well off as they would have been in regular old prisoner's dilemma, and then they get to enjoy all the benefits. That would be like on this axis or on this axis. You're just as well off as you were at prisoner's dilemma, and I got all these new goodies. There's no rule that says the institution has to generate a symmetric egalitarian outcome. And who determines the terms of the institution? In general international relations, it's the powerful states. I'm not sure if you noticed, but the United Nations doesn't exactly say, let's just scrap the status quo. International institutions reflect power, but it's bounded by this set of possibilities. That is the current understanding for a lot of folks in terms of what an institution is and what it does. Is it uses this folk theorem logic of equilibrium selection. It says, you know what? We have this embarrassingly large set of possibilities. We have squared the circle, we have saved ourselves from the awfulness of prisoner's dilemma, and now what? It's a huge point. That's a beauty. It doesn't get much better than that. Now look, no free lunches. This is both a happy result and a sad one. Because there is no best way to know how to navigate this giant set of possibilities. It's natural to, just the same way as bargaining week, both times that we did it, it's natural to say, well, let's try to get to the frontier, the Pareto frontier of this thing. And then maybe we'll talk about egalitarianism with respect to power dynamics or something like that. But there's no rule that says that it has to be on the frontier. This is theoretically rich. And to be honest with you, even though there's been a lot of work on the subject, I don't think enough things have been said about how we're going to navigate this particular situation. How an institution designs happiness across all of these states. Nevertheless, I hope that this is a point that sticks with you because it's a real beauty. The infinitely repeated prisoner's dilemma, the way that we take a sad story and turn it into a happy story, and then the responsibility that creates. All this because of patience and the possibility of breakdown. It doesn't get any better than that. This is what IR theory is here for, is to help you to think about that thing that way. To help you to see it. It doesn't get any better than that. And I hate this, but it doesn't get any better than that. That's gorgeous and it's ugly. Oh, I gotta get over this contradiction thing. So that's how the shadow of the future both creates opportunities for happiness and induces real responsibilities for purposes of institutional design. So what are we talking about today? Well, this is a very venerable idea. This is something that I think every IR student ought to see. What's annoying is that it's easy just to allude to this. A lot of people just allude to infinitely repeated prisoner's dilemma. They allude to the analysis. They allude to tit-for-tat. They allude to grim trigger. And that's fine. But the results are simple enough and intuitive enough that there's no reason to just allude to it. It's good to see it. And when you see it, you appreciate that there are subtleties and wrinkles that might not be as obvious as one might expect, particularly given how stark the prisoner's dilemma ends when we tell it in a static way. This is one of those core teachings that any IR student ought to see, but I think more importantly, any student in a class like this ought to be able to at least know what it looks like, even if you couldn't perform the analysis by yourself just off the top of your head, which is fine. What's interesting about this is it seems like there's some hubris. It seems as if we're imposing some unrealistic thing with this infinite time horizon. And then in the earlier parts of today's lecture, we realized that actually a lot of this were aspects of modeling humility, where we don't know the end of time, and so we proceed as if infinite. And we don't know the actual patience level, but it actually represents some internal probability of breakdown. We saw that with clever workarounds, we were able to think about repeated interaction like states and leaders of states experience without having to issue too many fiats about when we thought the end of time was, or when we thought the actual breakdown of some interaction would be, or something like that just, quite frankly, is beyond any analyst's grasp. I also think it's fun to see infinitely repeated prisoner's dilemma because the folk theorem ending there is such an avenue for creativity. To think about all of the possible ways that we could design an institution to try to come up with some desired outcome in terms of utility imputations. One, that highlights the importance of utility theory as we learned it early in the class. To be able to talk in terms of happiness units really greatly simplifies that task, because there's no way we could try to take it on if it was really about just the choices, or if it was really just about the preference. It's just nice to be able to talk in terms of the happiness numbers and know that that's a good single currency to think about. But it is important to remain humble, and it's with that notion of humility in mind that I'd like to conclude with a provocative thought. So the next step from something like a repeated game, like I taught you today, is what you might call a stochastic game, where, we're playing Prisoner's Dilemma today, and then conditional on what we do, we might play Prisoner's Dilemma tomorrow, or we might play Chicken tomorrow, or we might play Assurance tomorrow. There's some set of probabilities that takes our actions today and then takes us to a new game tomorrow, right? And it might be the same game and it might not. Essentially, what we've been studying today is a game where we play Prisoner's Dilemma, and irrespective of our choices, we play Prisoner's Dilemma again tomorrow. There's no particular reason to think that the terms of the game, the structure of the strategic interdependence, will be the same tomorrow as they were today. And importantly, there's no reason to believe that what strategic interdependence we have tomorrow will not depend on what we did today. If we defect on one another a lot, if we defect on each other today, then there's no reason to think that we're going to wake up in some new sunshiny stag hunt world tomorrow where everything is rosy. So in other words, we as the writers of the fables, it's an act of hubris for us to say, and it's going to be that way every day for the rest of time. That transcends the probability of breakdown thing. That transcends the impatience thing, right? If you don't know what the world is going to look like tomorrow, it's awfully bold for you to say that it's going to be Prisoner's Dilemma every day for the rest of time. And that your players don't have any say in that through their own actions. They can't try to influence what the terms of the game will be tomorrow through their actions today. We have made them very weak in that sense. They have no agency over what the strategic structure will be moving forward. So that seems unhumble, and I think that's bad, but this is just an introductory model, and it's fine. But the next step up is to try to be a little bit more humble about that, too. But having that in mind then introduces the question of how much are leaders of countries aware, not just of the strategic structure of the international system in the moment, but also in what the strategic structure will look like tomorrow, and how their choices tomorrow will influence that. So leaders know more about themselves than we analysts could ever hope to. We're just trying to explain their behavior as best we can to ourselves, to students, to other scholars through journals, and so on. We don't really know what's going on in the inner workings of any leader's mind, or within any massive bureaucratic department at state or defense or anything like that. So we have to really strike an important balance. We don't want to model so hard that there's no way that leaders or states could influence the future. but we don't want to model with so much flexibility that we suddenly equip them with way more awareness than they have. So what's the appropriate amount of modeling humility? And what does that mean for how humble we should feel about our own conclusions as we draw them, not as analysts, but just as people that care a lot about international relations? Now, if you ask me, the answer is we should always be maximally humble about things. I think that we know less than we think that we know. That's just because I went bald when I was 16, I just have a generally unrosy view of things. But I think that that's more than just erring on the safe side. If there's anything you learn from playing the stock market or anything like that, it's that no matter how many variables you think you can include, there will be one more. Even if a variable shouldn't matter, even if you have thought through how much a variable should or should not matter in a particular interaction, you're not the one that decides that. The leaders are, the countries are, the people at the United Nations are, the rebel groups are, the firms are, the consumers are. They are the ones that decide what matters and what does not. No matter how much something seems like it should or should not matter for the shadow of the future, it's not ours to say, right? And those variables that don't matter, those variables that shouldn't matter but don't, can introduce all sorts of interesting volatility in these dynamic interactions. There's all these variables that people think matter. People, so nationalism is one that comes to mind, right? So if I'm on a battlefield and I think that my country is the best of all countries, that's not going to make the bullet fly any straighter. But that doesn't mean that I can still make choices based on that belief, even though it ends up not having any true effect on how straight my bullets fly. And because of that, because at any point in time, somebody with actual agency might think that something matters, even though I, the analyst, feel that it should not, that means I have to be very humble about the inferences that I can draw, both about what really matters in international relations, but also about what's going to be happening in the future. Because some variable that I'd had no idea could matter could change everything. Rational actors, the robots that we draw, can still be subject to the whims of self-fulfilling prophecy. They are still subject to the powers of animal spirits. They are still flesh and blood even though they are robots. And that forces us to be humble. You may then be wondering, why did I write down an infinitely repeated prisoner's dilemma where I said that I knew the terms of the game every day for the rest of time? The answer is, I wanted to show you a cool story. I wanted to start from a sad story like the prisoner's dilemma in a static sense, and show you how to turn it into a happy story by thinking hard about an important substantive feature like the future. But to act as if the future is then a silver bullet that allows me to do whatever I want to, I would be doing you a grave disservice if I told you that that was a reasonable way to proceed as a modeler, as an analyst, or as somebody that reads the newspaper. Nobody knows. Nobody knows. Now, I say nobody knows a lot. I have a generally sad view about the world and how we interpret it. But the bigger lesson is nobody knows, and that's okay. All these little lessons that we do, all these exercises that we do, all these, even if the infinitely repeated prisoner's dilemma isn't the right way to proceed, it's comically wrong. Digging in the dirt gets you something. So that whenever you learn what the thing that actually does wind up mattering is, you'll be ready for it. Nobody is saying that this is how it is. We're just trying to help you to think in a principled way about these things. And maintaining principled humility, not I think we're wrong all the time, and not I think we're right all the time, but actually acknowledging the strengths and weaknesses of our understanding of things, that's super duper important because international relations is not getting any simpler on our account, if you haven't noticed. Every day seems more uncertain than the last. My view of education is that not that it should equip you with any particular set of skills, which it should, but also that it ought to transform you. You should come out a better person than you were when you started it. And there's no guarantees of that, but it's a hope. And these fables play a really big part in that. And being able to tell them in this unified way, to be able to start from rationality, turn rationality into collective rationality, turn collective rationality into the prisoner's dilemma, turn the prisoner's dilemma into the infinitely repeated prisoner's dilemma, to go from some knowable axiom and to take it to this wonderful and sublime substantive point that you got showed today. It's not because we think that point is true, but because we wanted to have a consistent approach that took you from axiom to sublime insight. I hope that that's something that you've gotten a taste for, because it really is about subjective taste about what kind of knowledge you think is useful. I think the kind of knowledge is useful that makes you ready for whatever's coming, because surely what we think we know about today isn't totally true. The shadow of the future looms large not just in our robots' lives, but on our own. Thanks for watching.